Okay, so hi and welcome. Can you hear me? Hello.
Yeah, hello.
Yeah, can you hear me? Okay. Okay, so basically today is our fourth number of class, and mainly today I also try to discuss about the some advanced topic on remote sensing analysis, such as LST monitoring and other advanced topics. So let's go. Just I simply share my screen. Okay, so now can you see my screen?
Yes.
Okay, so let's go. Yeah. Okay, so basically today I try to discuss about that how we can easily remove the cloud from the satellite imagery, mainly Landsat and Sentinel. How we can easily remove the different types of cloud and also remove the different types of haze from the satellite images and get the very clear satellite images. Okay, and we also try to discuss about the DEM data and using the DEM data how we can easily make the different types of hillshade map, salt map, aspect map, as well as we also try to discuss about the land surface temperature monitoring from Landsat satellite imagery, how we can easily create the LST map, as well as we also try to discuss about the how to calculate average, maximum, minimum NDVI value for any specific region. Not only for the NDVI, using this process we can easily calculate it for any specific region for average, maximum, minimum, NDVI or LST or anything for any average, maximum, and minimum pixel value. How we can easily calculate. Okay, so let's go. So first of all, I try to discuss about that LST monitoring. How we can easily make the LST monitoring using the Landsat imagery and make the LST map. So for that, I simply open some research paper, then try to show you the algorithm for that LST. Suppose the Landsat 8 imagery. Okay. Okay, suppose I simply open this paper. Okay. Yeah, so basically, this is the LST monitoring using Landsat 8 satellite imagery for the Batna city in eastern Algeria region. So in this time, in this paper, you can see the all of their follow chart about their work. So mainly they use here the Landsat 8 satellite data, and from there they take the near infrared band and also red band, and also take the thermal infrared band, mainly band 10 is a thermal infrared band. So in this time they are calculated using the near infrared and red. This band they are calculated for NDVI, normalized difference vegetation index. From here, using their NDVI, they calculated the fractional vegetation. It is also called the vegetation proportion. Calculated the vegetation proportion. Okay. After that, from here they calculated the surface emissivity from the vegetation proportion. Okay. So then apply the mono window algorithm and then calculated the LST. Okay. So this is the paper. I also send you the paper. You also read about the paper. Then you can easily get all of those idea for that. What is the algorithm for LST using the Landsat 8 satellite imagery. So basically you can see all of those things in here. So in this time we just follow this paper and then calculated the LST. Okay. So first of all, you can see the algorithm about this paper. Okay. So I simply open my code editor and try to write the code. I'll just open this code for that. And first of all, check the output about the result. Then I describe about all of this code and how it will be work. So this is our study area, and all of this layer here I add. First of all, you can see it loaded all of this layer one by one. So here you can see the first, it's showing the LST. So mainly this type of red color identify about the highest LST. Okay, and blue color is the lowest. So you can get the LST. This is the LST map. Then it's the emissivity or EMM. Okay, then it's the fractional vegetation. It is the thermal band, and it's the NDVI map. And this is our satellite imagery. Okay, so this is our satellite imagery for the year of 2020. And from that we calculated the NDVI map, and this is our thermal infrared band. Using the thermal infrared band, we after that from the NDVI we calculated the fractional vegetation. It's a fractional vegetation without color. It's showing as a gray color skull. There is no problem. After that we calculated the EMM or emissivity about this, the result about that. And from here we use here the mono window algorithm and then make the LST map. So this is our LST map. So now how it will be work, I describe one by one. So let's go. So first of all, here you can see this is my study area, Dhaka city shapefile. It's my study area. So basically in this time, I simply go to my asset. Suppose Dhaka city. I click on here the Dhaka city, and in this time we can import the boundary shapefile in my asset the two way. One way is that you can simply click to the import. Suppose I click to the import, it imported. You can see it imported. Okay. Another way is that simply click on here, and then it also provide about the ID. You can see table ID. Okay, just simply copy the table ID, and then suppose you can take the any variable name. Suppose I put the variable name is that ROI, and then use here the e dot feature collection, and then paste this ID in here. Okay, so these are two way for importing the shapefile or boundary shapefile. You can import it in Google Earth Engine platform two way. One is that simply click on here and then import. It will be imported. Or copy this table ID and then paste here. Okay. And before that, use here the e.feature collection. Okay. So first, I already imported my boundary. Dhaka city boundary, I imported. And give the variable name is that geometry. Okay. We can use any variable name. There is no problem. So here in this code, I just simply imported my boundary shapefile of Dhaka city. And then I can simply show the result for the center focus of the geometry. And this is the code for removing the cloud and haze from the satellite Landsat 8 satellite imagery. And how it will be work in this time I discuss about this topic, then move in here. So for that, simply open a new code editor, how to remove the cloud and haze from the satellite images. Then we describe about this code. Then you can easily understand about the code. Okay, so let's go. How to remove cloud and haze and get the clear condition of the satellite images. So in this time here I use the Landsat 8 imagery. So that's why in this time I show you the for Sentinel imagery. Okay, then both of things you can easily relate it and you can easily work with that. Okay, so first of all, I simply import a image collection, Sentinel-2. Suppose this is my image collection, I simply import. Okay, so it is an image collection. So I simply import my image collection. I put the name, suppose S2. Okay, we can put any name. There is no limitation about that. So Now this image collection I need to filter for my specific region of interest in Dhaka city. I put this name as suppose RY. Okay. So now take a variable. Suppose I put the variable name is the image, and then use at the S2 image collection and use at the filter bounds with my area of interest RY, and then give a specific time period. Suppose I put this image for 2016 for 2016 December 31. Then I put this time period look like that. After that, I also put here the another thing is the filter metadata, and put here the image properties. So just I simply go to this window and give the image properties. Suppose cloud pixel percentage. So this is my image properties. Simply copy and paste and put here the suppose less than suppose 1% cloud cover. And all of those images I just make a median image collection, median, and it's clip with my boundary. Boundary is that ROI. So now let's check the image. So just use here the map.addLayer function and use the image and also center of the shapefile map.center object. Object is that ROI, and then suppose zoom level 8 and click to run. Okay, so it is the lowercase ROI. Click to run. So now we display the image. We can get the image look like that. Okay, so now I set the visualization about this image. So click on here. Such as I put the band combination such as red, then green and blue. Custom 98%. Apply. As well as also import the visualization. Simply copy. And this variable just paste after the object name. Okay, now it's set it. We can get the images look like that. Okay, so in this time this image is not much cloudy. Okay, so mainly when I increase the cloud, when I increase the value, in this time I put at the less than 1%. Suppose I put at the less than 90%. Then I find out the some cloudy pixel value in my satellite images. You can see. Yeah. So in this time here you can see this is the our result. We can get the some cloudy pixel. Okay, this type of cloudy pixel we can get in here after increasing the value 90%. Basically in this time it take all of those images which is the less than 90% cloud cover. Okay, so that's why in this time you can say I can get this type of cloudy pixel value. Okay, so now anyhow I need to remove this type of cloud and also remove this type of haze. Okay, using the cloud marks function. Okay, so in this time here you can see the one kind of function, this function called the I simply open this image collection. You can see it has the band about that cloud marks band. You can see. Yeah. There is a cloud marks band. Okay, so in this time I need to use this band for Sentinel-2 QS60 band. Okay, I need to use this band and then remove all of those unnecessary pixel values such as cloud and also remove the haze. Okay, so it's a QS60 band. It is a cloud marks band, and QS60 has some bit. Okay, you can see bit 0 to 9 it unused, and bit 10 it's a cloud, and this bit 10 have a two signal. One is 0 and another is the 1. 0 means that no clouds, 1 means that cloud present. Okay, as well as also you can see the bit 11 it is a cirrus cloud. 0 means that no cirrus cloud and 1 means that cirrus cloud present. Okay, so in this time I need to use this type of bit and then set equal to 0. 0 means that no clear condition. You can see bit 10 for 0 no cloud, bit 11 for 0 no cirrus cloud. Okay, so bit 10 I need to select 0, and also bit 11 need to select 0, which is indicating the clear condition of satellite images. Okay, so in this time I write my function. So first of all, I need to choose this band QA60. So mainly it's a cloud marks band. Okay, this cloud marks band I need to use, and then select the bit 10 and bit 11. From bit 10, I need to select 0 signal, and also bit 11 need to select 0 signal. Okay, which means that no cirrus cloud. So let's go how I can work for that. Simply copy this band, and I need to write a function about that for writing that. So for writing this function, first of all, take a variable. Suppose I put the variable name is that marks to clouds. You can put any variable name. Then make a function keyword and put the element name, suppose image. In this curly bracket, you can simply put your argument. In this time, my first argument is that I have to select this band, QA60 band. So take a variable, suppose QA, you can use any variable name. Then use here the element name. So basically, this element name I use in here, and then use the select function, select this band QA60. So now I select the band QA60. And QA60, this band have a 2-bit, bit 11 and bit 10. This band has a 2-bit. In this time, I need to select the 2-bit, bit 10 and bit 11. You can see the result about that. Bit 10 and bit 11, because in this time only for the bit 10 and bit 11 has a signal, because 0 to 9 it unused, don't need. So only for need the bit 10 and bit 11. Okay, so for that, in this time I need to select bit number, bit 10 and bit 11 I need to select. For bit number select, we have to use a symbol. So take a variable, suppose I put the bit is that cloud bit marks, I put this variable name, and in this time use here the 1 less than this symbol we have to use, and then put here the bit number. What is the bit? Bit number is the 10. I select the bit 10. After that, we have another bit, bit 11. So take the another variable, cirrus, suppose cirrus bit max, and then put here the 1 less than 11. Okay, so this is the symbol for selecting the bit 10 and bit 11. Always put here the 1 and then put here the bit number. Okay, put here the 1 and then put here the bit number. So 10 and 11 is our bit number. So in this time, from bit 10, I need to select the 0 signal. 0 means that 0 signal. Okay, signal, you can see signal means that we have the 2 signal, 0 and 1. So in this time, from bit 10, I need to select the 0 signal, which means clear condition. You can see bit 10 0 and bit 11 also 0, which means that is the no cloud. So for that, I simply select the bit 10 and bit 10 and 11. After that, select the bit signal. Okay, for selecting the signal, take a variable, suppose marks. You can use any variable name. And first of all, we have to select the band. Okay, so basically this bit 10 and bit 11 come from this band, QA60 band. Okay, and QA60 band is stored in a variable QA. Just simply copy the QA, and in this time you just connect the bit with the band. So it's QA, it's a band. Okay, this is a band, QA60 band. This band I need to connect with the cloud bit marks, mainly 10. Okay, so for connecting that, we have to use a function. This function called the bit wise end. The bit wise end, and then simply copy this variable name, cloud bit marks, copy and paste. And after that, set equal to 0. Okay, it's the equal. EQ means equal. So in this time I select the signal 0. 0 number signal I select. Okay, and we have another band for 11, another bit for 11. So QA, I call the band QA60 and just connect the bit number. So use at the bitwise and function and then call this Siraj bitmax and paste here and set equal to zero signal. Okay, so in this time it's my condition. What's my condition? I select the band of cloud marks band QA60. From here select the bit 10, then equal to signal 0, and also call my band QA and select the Siraj bitmax, which is the 11, and set equal to 0. So it's identify or indicating the clear condition of your satellite imagery. So now how I can apply it? So this is my condition. Okay, so every function we have return. Okay, so final output we have to return. So in this time I what I return from this function. So for the user, the return function return this image update condition. Okay, this image is updating according this condition. So signal 0, both of flag will be 0. Okay, both of signal will be 0. So this condition I need to apply and update my image. So for that, in this time I simply copy this variable name because this condition is stored in this variable marks and simply paste in here. So now this function is ready. Okay, now this function is ready. Okay, so now I can easily use this function and remove the cloud. So now I also compared this code in here. You can see I already write the code about that. So in this time we are use the same code in here. So in this time, first of all, you can see mainly it's the Landsat imagery. So for the Landsat imagery, I simply open the image collection and show you the result. Suppose this is my image collection. Simply copy and then show you the what is the cloud marks band for the Landsat 8. Just simply open the band and you can see the result for that Landsat. You can see what is the band. This band name is that Pixel QA. Okay. So basically in this time for Landsat, it's the Pixel QA band. And for Sentinel, it's called the QA60 band. Okay. So in this time, it's our Pixel QA band. And you can see the Pixel QA band has some bit number. Bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 7 to 6. All of those bit number is available in here. So in this time, I choose the Pixel QA band and then select my specific bit number and set equal to 0. Okay, which identify no, there is the no cloud, there is the no cloud shadow. It's identify about that. Okay, signal 0 signal. I have to choose the 0 signal from here. So in this time here you can see I already write the code in here for removing the cloud. Okay, so in this time you can see it is the function and it's a variable name. Okay, so in this time they are just used at the function keyword and put this variable name. It is the one way, but another way is that you can simply copy the variable name and then use here the var keyword and paste the variable name. And so this is the another way for identify the function. We can write the function in JavaScript in the two way. One is that without var keyword and another is the use the var keyword. You can see this is the another way. So it's another way. Okay, so it's another way to create the function without var keyword. In this time there is a no var keyword, but in this time what is the function variable name? Function variable name is that this is the function variable name max l8sr. It's the function variable name. But if you want, you can also use the var keyword. There is no problem. Suppose I use the var keyword. Okay, so this is the var keyword I simply use. Okay, so in this time it's my function variable name, then equal sign and put here the function keyword. In this time I use here the element name is the collection col. Okay, that's used. You can use any name, there is no problem. And then I have to select the 2 bit, bit 3 and bit 5. Bit 3 is the cloud shadow and bit 5 is the cloud. You can check it from here, cloud and cloud shadow, because I want to remove the cloud and cloud shadow from my satellite images and get the clear condition of the satellite images for Landsat. You can see bit 3 is the cloud shadow and bit 5 is the cloud. Okay, so I select the bit 3 and bit 5. Okay, bit 3 and bit 5 selected, bit 3 and bit 5. And how we can easily select the bit? Just take a variable name and then use at the 1 less than 3. 3 is the bit number of cloud shadow and bit 5 is the bit number of cloud. Okay, and then also need to select the pixel QA band. Okay, so for that, take a variable QA and select here, select pixel QA band. And now we just set equal to 0. Both of bit set equal to 0. Same function which I write in here. Same function in this time we also write in here. And then return for update marks. My collection, I need to update marks function. Then simply copy this variable name and paste here. So now this function is ready to remove this type of cloud and cloud shadow from this satellite images. Okay, so his function I write in here, I use the same function, but the band name and bit number is different for the Landsat. Okay, and it's the Sentinel. Okay, so now my function is ready. So now I just need to connect this function with my satellite images. Then all of those cloud will be removed and we can get the very clear satellite imagery. Okay, so let's go how it will work. So for that, I just simply copy the same image collection from here. Simply copy and paste here. Okay, and I simply change the variable name. So it's a image. I put the variable name is the image cloud free. Okay, it can be any name. And then how I can add that? Just simply use here the map function, and call my function variable name. Okay, so what is my function variable name? You can see my function variable name is that marks to clouds. Simply copy and then paste here. After that, simply copy these things from here and paste. Okay, I put the layer name. Suppose this layer name is the cloud free. Click the run. In this time, we can get the clear condition of the satellite images and all of those unnecessary cloud pixel will be removed from here. Resume. And show the result about that. We can see the one layer is this the
Sir, good evening, sir. Hello.
please.
Hello.
Yeah, you have any question?
Yeah. Sir, are you audible my voice?
Yeah, I can hear you.
Yeah. Sir, what is the objective, sir? I was 10 minutes late joined actually. What is the objective you are
Okay,
doing
so
now? This
so basically
pixel,
today we discuss about the LST, how you can easily make the LST, how to remove the cloud from the satellite images, and how to calculate for average, maximum, and minimum pixel value. Okay.
but here cloud pixel removing means removing methodology is where you are talking from, where you are referring this methodology, sir? Because cloud removing means you are doing atmospheric correction.
Yeah. Okay. In this time, they are using the CF max algorithm. Okay, for removing this type of CF max.
CF max.
Yeah. We can check about this algorithm. They are also mentioned about the algorithm in Google Earth Engine. They are used here. Yeah, again, CF max algorithm for pixel quality attribute generate from the CF max algorithm. And then remove.
Oh, it is not an atmospheric correction.
No, it's not a
it's not improvement correction.
Yes. So you can see in this time we can
have an idea about how to apply atmospheric correction, sir?
In this time, it's not for the atmospheric correction, because all of those satellite images, you can check the information, they're already atmospherically corrected. Okay, so you can check the
No,
information. Suppose you can see this is the image, and go to the description about the images. Okay, then you can get the result. You can see that they're already all of those images. It can be Landsat, Sentinel. All of those images is automatically atmospherically corrected.
so L2 product you are saying, sir?
You can see this data set is the atmospherically corrected. Okay, so it already atmospherically corrected. So that's why in this time, when you use from the dataset from the Google Earth Engine platform, you don't do down atmospheric correction. But when you download the data from the Earth Explorer or USGS, then we have to apply the atmospheric corrected. Okay.
Okay, sir.
Okay, it's already done all of those data set, and you can see this. They are already including the cloud and shadow, water, snow marks produced using the CF marks function. And what is the CF marks you want to download? Just simply click on it. You can get all of those algorithm how it will be work. Okay. So just read the description about the data set, and you can easily get the idea about the how to generate the data. About it. Okay, so it already is. So in this time, you can see how we can get this type of images. So you can see it is the cloud pixel. You can first off, I can get the cloud, but after applying the cloud marks function, you can see we can get the very clear satellite imagery. Okay, this cloud will be removed. We can get the, and all of those haze also removed from here. We can get the very clear satellite images, and now we can easily use the image for different types of analysis. Okay, so in this time, we also apply the same approach in this here. Okay, same, just change the bit and bit number, and also change the band name of the pixel QA band. Just simply use this band name. Okay, so I hope you can understand about the code, how it will work. Okay, so now after that, I can see first of all I create this composite. Okay, so this is my image about the Landsat 8 imagery, surface reflected imagery. So just I display about the result in here. Okay, so you can see just use the map function and call this function variable name. Okay, for the cloud marks function variable name, I use here this name for the marks L8SR. So this variable name, just I simply use the map function and copy and paste. Then it will be added this image and remove all of this unnecessary pixel value from here. Okay, then simply take the image for this time period. I use this time period, and after that filter bound with my shapefile. Filter bounds with my shapefile is the geometry. Okay, so after that I create the median image collection. Okay, so all of those images after collection, I just use here the median and clip with my shapefile, and now it getting the image look like that. I use here the map.add layer function and show the image. I can get the image look like that. So this is my image, and it contains all of those band. All of those band it contains. So in this time, first of all, I need the two band. One band is that near infrared band and red band. Okay, because you can see our algorithm, we have to need the two band, near infrared band and red band. From that we calculated the NDVI. Okay, so question please. Yeah.
Sir, actually I was just asking that can you start once again this total algorithm of LST?
Okay, don't understand you. Yeah, please again.
Sir, my voice is clear?
Yeah, now clear.
Okay. Sir, I just wanted to ask that can you explain this flow chart once again, the whole process of LST?
Okay, I understand. Okay, no problem, no problem. Okay, so you can check about the result one by one. You can understand about that. Okay, so first of all, you have to calculate the NDVI. Okay, so just use the NDVI. So mainly NDVI, we have to need the near infrared band and red band. Okay, near infrared band and red band. Okay, so I simply call my image. Okay, you can see it's my variable name image. It is stored at the median image collection. This image is stored in this variable. Just use the image and use the normalized difference function and calculated the normalized difference between near infrared band and red band. Okay, just I calculated the NDVI. Simple process. And previous class I discussed about the lot of time for the normalized difference function and other types of method. Already show you that. Okay, so now I display the image of the NDVI. So you can see I simply add the image of NDVI. So this is the NDVI. Okay, it's my NDVI map. After that, from this NDVI, and then we have to set the another band. It's called the band 10. Okay, so band 10, mainly this band 10 is the brightness temperature band. You can see the band 10. You can see band 10. Okay, so it's mainly the band 10. It's called the brightness temperature band, and this band, originally collected with the resolution of the 100 meter per pixel, has been resampled using the cubic convolution to 30 meter. So 30 meter, and this unit is the Kelvin. Okay, and it's the scale factor about this band 0.1. It's a scale factor of the band 10. Okay, so in this time I need to select, basically it's my thermal band. Band 10 is the thermal band. So in this time I use this thermal band, just simply use the band in here. You can see I simply call my image, because this image stored all of those band. From here I just select only for the thermal band B10, and then for reprojected the scale value, just simply multiply with my scale factor 0.1. Okay, so just simply multiply with the 0.1. Okay, after that I display the about the thermal band. This is a thermal band. We can get the thermal band. Okay, so we can get the thermal band also in here. After that, in this time I discuss about that how we can easily calculate for minimum and maximum any pixel value, because for the next step I need to discuss about that minimum and maximum NDVI. Okay, I already create the NDVI map, but I need the minimum and maximum value of the NDVI map from here. So now I discuss about the topic how we can easily calculate for any pixel value for average, maximum, and minimum. So just I open a new code editor. So after that, I can describe this code in here, how to work for the find the minimum, maximum. Then you can easily relate it about this code and easily understand about that. So that's why in this time, okay, just I open a new code editor and then make any types of map. Suppose I create the NDVI map or any map. From this map, I just calculate what is the minimum, maximum, or average value of NDVI, or average value of the LST, or anything. How we can calculate for any pixel value, we generate the average, maximum, minimum result. So let's go about that. Average, then maximum, minimum, pixel value for any specific region. Okay, so this time I talk about that. Okay, so for that, suppose I simply open this Dhaka boundary shape file and put this name such as a RY. Okay, and also just open a image collection such as Landsat image collection. I simply open, or Sentinel, anyone, no problem. But all of these things will be same process. Suppose from the Sentinel, I just work for the Sentinel-2 multi-spectral instrument. And from here, suppose I work for the top of atmospheric. Then simply copy. And give a variable name, suppose yes. Then filter it. Suppose use the filter bounds function. Filter bounds with RY. And then use here the filter, suppose filter date. Is that 2020, 1st January from 2020, December 31. And I take only for the filter metadata such as simply copy the image properties from here. Suppose cloud pixel percentage, simply copy and paste. Place them, suppose 1. All of this image I just make the median composite and click with my shapefile is that ROI. And I also calculate using the image for making the NDVI or anything. Suppose take a variable NDVI, call the image, and use at the normalized. Normalized difference between near infrared band and red band. So near infrared band is the B8 and red band is the B4. You can check the band in here, B4 and B8. After that, it calculated. So just for the result, map.add layer and NDVI. I display the result such as mean. It will be suppose -1 to max, +1. Color plated. I make the color such as blue, then suppose white, and finally suppose green. Loaded. For the focusing, use at the map dot center object. Object is that ROI, and then 10 and click the run. So you can get the result look like that. NDVI map. And when you see the better visualization about that, just click on here and then stress 98%, and it produce a mean max value. Simply copy. Suppose it's negative, and also copy the positive value and paste here. So now click to the run and then check the result about that. Okay, then we can get the better result about the vegetation. Okay. So now from I calculate the vegetation map about that. I can say click on here and then suppose click on the vegetation. 0.5 we can get in here. Okay. So now from this map, I just need to calculate what is the maximum NDVI value for this map. What is the minimum NDVI value for this map? What is the average value for this map? I need to calculate for this result. For calculating that, how I can calculate? So in this time, we have to use a function. This function called the reduce region. Okay, so reduce region we have to use. So just take a variable. Suppose max NDVI. You can use any variable name, and then call this NDVI. Simply copy this variable and paste here, and use the function reduce region. Okay, so basically this reduce region is a function. This function mainly calculated for any specific region for average, maximum, minimum, or any statistical value, pixel value. Then make a dictionary, curly bracket start, and also curly bracket int. So first of all, reducer. So in this time I calculate the maximum value. Use at the EE dot reducer dot max. Geometry is our specific boundary. It's the RY. Scale is the resolution of satellite imagery 30 meter. Then it's not asking about that. So now just simply print the result. So use at the print max NDVI. Click to the run. In this time, for the region of interest in Dhaka city, what is the maximum NDVI? We can get the value. We can get the 0.6. It is the highest value for this region of interest for the NDVI pixel value. In this time, we can see we can get the result as a list or dictionary. So basically, it's showing the result as a dictionary. Dictionary means that keyword and key value. So it's a dictionary. So I just need the value without dictionary. I don't need any types of dictionary. Keyword and key value I don't need. I just need only for the value. So for getting this value, we have to use a function. This function called the values and then get 0. In this time you can see what happened. In this time it generate only for the value without dictionary. When I put here the values and get 0, it just print only for the value. Okay, without, you can see it showing as a dictionary keyword and key value, but I don't need for in types of dictionary. I need only for the value. So for that I use values. From here use the get function, get 0. Click to the run. Click to the run. In this time you can see it just generate only for the value. Okay, we can get the value. Suppose I calculated the minimum NDVI value, just simply copy the same code and paste here and put here the value, suppose min, mean. Suppose I change the variable name, so I put the variable name is the mean NDVI, then copy and paste and click run. In this time it generate only for the minimum NDVI value. It's computed. You can get the minimum NDVI value. It is the minimum NDVI value and it is the maximum NDVI value for this region. I calculated the average. Simply copy and paste and use here the mean and also put here the another value, suppose mean NDVI. Simply copy and click the run. In this time it generated the result for mean NDVI. We can get the result look like that for the average result about that, as well as so in this time we just apply the same approach in this code for find the mean and max value. And why I need the mean and max value? Why? Because you can see the another term in this paper. It's called the vegetation proportion or fractional vegetation. For calculating this equation or vegetation proportion, we have to use the find out the mean and maximum value of NDVI. So for that we need to function or same equation and then calculate the result of fractional vegetation or vegetation proportion. Okay, so for that what we can do, you can see just we simply find out the mean and max value of NDVI. Just find out the mean and max value of NDVI. So just use here the NDVI reduce region. Okay, mean geometry, same code we just use here the first find out the mean and use here the values and get. Okay, in this time max pixel value is not mandatory. If you want you can use it, it's optional value. Okay, it's optional. If you want you can use it or don't use, there is no problem. It's optional argument. And same approach for the maximum, just calculated the maximum NDVI. Same approach, calculate the maximum NDVI. Okay, so in this time we talk about the fractional vegetation. Okay, for the fractional vegetation, NDVI subtract with mean value divided by maximum subtract with mean value and power to the power 2. Okay, so it is a whole square. Just same equation. You can see same equation you can apply in here. Okay, so now we can get the result about the fractional vegetation using the formula fractional vegetation and display the result about the fractional. This is thermal, it's a fractional. Okay, so it's a fractional formula we can get in here. So it is a fractional vegetation. Okay, so after that we have to calculate the emissivity about that. Okay, and now what is the formula about the emissivity? So for the formula is that you can see the emissivity formula, we can get the two types of formula. Okay, so emissivity formula is the town and also natural. Okay, so when you want to calculate the NDVI for the town and natural, this type of value, it's the constant value, this type of value will be changed. Okay, so you can see in this time for the emissivity for the town, they are used here this constant value and also use here this constant value. It's multiplied with the fractional vegetation, subtract with this constant value, multiply with the fractional vegetation. Also you can see for the natural body, they are used here this constant value and addition with this constant value multiply with the fractional vegetation, which I already calculated for the fractional vegetation, and negative subtract with this value, constant value, and so it's a constant value about that. And also you can get this how they can get this formula. You can get the citation about this type of paper. Then you can easily get a lot of idea about that, how they generate this type of formula. Okay, so now in this time we just define here our constant value a and b. You can simply define A is the 0.004, b is the 0.986. Okay, so in this time fractional vegetation multiply with a and add with b, okay, and rename it EMM or emissivity. So now we can show the result about the EMM. The EMM result without color, it's showing as a gray color. Okay, so after that we have to calculate the LST. Okay, and this LST, it is a formula about the LST. TB means the thermal band. Thermal band, it's divide. Sorry, you can see the thermal band and divided by full equation. It's a full equation from here. Okay, so 1 plus, it is a constant value 0.015 constant value, multiply with TB thermal band divided by, it's also constant value, log EP. Okay, log EP emissivity. Okay, log with EP, it means the emissivity. So in this time, just you can see I simply call the thermal band. Okay, and this expression come from the thermal band. So that's why I already calculated make the thermal band. You can see another layer in here. I already calculated the thermal. Okay, in this time, in this thermal, I just use here the expression function. So thermal expression. So this is my equation for the LST calculation. This is my equation for the LST. Okay, so first of all, I simply TB is the thermal band, mainly is the B10. Okay, and EP, what is the EP? EP is that EMM or emissivity band. Okay, and here you can see 273.15 because it is a Kelvin. When I simply subtract the value 273.15, then we can get the result in degree Celsius. Okay, so now finally we display the result about the LST. So we put here the mean and max value about the LST 20 degrees Celsius to 29 degrees Celsius, and also display this type of color plated, and finally we display the result look like that for LST map. Okay, so now any question you can ask me about that. Any question or any doubt you can ask me for the full code. The first step I again explain. First step we just calculated the NDVI. From the satellite images we calculated the NDVI. Okay, so after the NDVI we calculated the fractional vegetation, and when you calculated the fractional vegetation we need the two value, minimum value and maximum value of NDVI. So that's why we have also need to find out the mean and max value, calculate the mean and max value. Okay, so after that we use the formula NDVI subtract with minimum value divided by maximum value subtract with minimum value power 2 or whole square, and rename it FV or fractional vegetation. Okay, so we can get the fractional vegetation. After that, using the fractional vegetation we calculated the emissivity, and this emissivity, this type of constant value will be different for the different region. It's not a fixed value, it's for natural body. You can check the lot of paper about that for LST. Suppose after completing the class you also try to check some paper for using the Landsat imagery. What's the formula they are using here? You can see the different paper have including the different types of formula or different types of constant value. Then you can easily get the better idea about that. Okay, for this constant value. So in this time we just calculate the emissivity using this formula. Okay, we can get the two types of emissivity we can get, and already calculated the fractional vegetation. After that, from the thermal band we calculated the full equation. Basically it's the equation for the LST. Okay, and when I just simply subtract the value 273.15, then it calculates the result in degree Celsius. We can get the result in degree Celsius. Okay, so just we use here the curly bracket and define what is the TB. TB means the thermal band B10, and what is the EP? EP means that EMM. I already created the EMM, and B10 I already defined about the result. So now finally show the result. We can get the result LST about this. Okay, so any question you can ask me. Yeah, please.
Yeah, okay. if I need to complete last step, so to get the air surface temperature.
What's average temperature?
Yeah, air temperature.
Don't understand your talk. It's the air temperature.
Yes.
Okay. So air temperature.
Air temperature from land surface temperature.
It's land surface temperature. Okay, not air.
Yes. Yeah, I know this land surface temperature, but how can get air surface temperature from this value?
Okay, for
I
the
think
air
it's a
temperature.
simple equation to continue.
Okay,
to get
for the air temperature, we
surface
have to use the another data set. Okay, for the air temperature.
another data set.
Yeah,
What
another
does it mean?
data set.
Another data set.
Another data set, there is a lot of data sets. Suppose you can also check about that. Suppose just okay, go to the data catalog and then find out.
I think only one equation to get the air temperature. Yeah, from land surface temperature.
Okay, for the Landsat, for the air temperature, first of all, you have to find out the algorithm. Just find out this type of paper, okay, for the reference paper. Then using this algorithm, you can easily calculate or any code you can write. There is no problem. First of all, you have to find out the paper. This paper, suppose there's a lot of way for that calculating the air temperature using the Landsat. So try to find out this paper, and in this paper, you have to understand about the algorithm. Okay, then simply write the code according to your algorithm. Then you can easily get the result for the air temperature. Not only for the air temperature, any algorithm, any remote sensing algorithm, we can easily implement in the coding in Google Earth Engine platform. Okay, just read some paper about the air temperature using Landsat imagery. Then you definitely you can get a lot of paper. Okay, from here, just choose the algorithm. Okay, then try to implement this algorithm in Google Earth Engine platform and then check the result. Okay, but you can find out a lot of paper about the air temperature using Landsat imagery. Yeah, please.
Sir, yesterday we seen Modi's land surface temperature.
Yes.
So we can we use directly that, or we have to process all this steps? Why we are performing this for more high resolution data? We are doing this.
Landsat, we have to use the high resolution data for Landsat.
تحفظ انت بس مالكش دعوه.
Landsat is better than Modis. Okay, so
Okay,
we
but
can get
final result is same. Means without comparison the resolution, only differences of resolution. Otherwise, these data set is equally same, no?
yeah, equally same, but basically we can get the proper accuracy for the high resolution imagery. We can get the better accuracy about the result because it is only for the 30 meter, but for the Modis it will be 1000 meter and 1 kilometer, and it's only for the 30 meter. Okay,
Okay,
so that's
okay,
why
okay.
in this time we can get the better result than Modis. Okay, so this is the process. You can see a lot of papers. Such as I will show the another paper for the LST monitoring. Suppose okay, you can see this is the one paper about that, as well as also land surface temperature. Rapid harmonization and land surface temperature using Sentinel-2 and Landsat 8 imagery. So you can see this is another paper about that. Monitoring land surface temperature impact on the land surface temperature using the time series for the remote sensing data. So you just read this type of paper, you can easily get a lot of information and lot of algorithm you can easily get, and then try to implement this algorithm in coding. Okay, then you can, it's the best practice for Google Earth Engine platform. Okay, so in this time we can get a lot of work in the research gate, this type of lot of work for the using the you can see monitoring LST and NDVI relationship. Okay, so this type of work you also try to do in Google Earth Engine platform, and then find out what is the relation for the LST and NDVI. So there are a lot of analysis you can easily do using the Google Earth Engine platform, and there are a lot of paper already published without Google Earth Engine platform. They are using here the other software such as ArcMap or QGIS or some traditional software they are used for creating the LST. But you can get the some few paper we can they are used here the LST for monitoring the using the Landsat imagery. They are used here the some very few paper, and also you can get a lot of paper. They are not using the Google Earth Engine platform. They are mainly used here the ArcMap software or QGIS software. Simply download this and then download about that. Okay, so you can get the lot of things, lot of paper in Google Earth Engine platform, and also read this paper and try to implement this type of code in Google Earth Engine platform. So it's the best practice about that. Then you can easily get the result. Okay, and also practice for the LST. So basically, this is the basic algorithm about the LST monitoring using the Landsat imagery. So using this process, you can easily make the LST for Landsat 5, Landsat 7, okay, also Landsat 9, okay. So in this time, using the same algorithm, I also assigned today. I also give you the previous recorded video class as well as the today's recorded video class, and you also try to use the Landsat 9 imagery or Landsat 8 imagery for year of 2021 or 23. Okay, in this time when you want to do that, you face a problem. Okay, so this problem I describe the next class inshallah about the problem, but you face the problem when you want to make the LST map for year of 2022 or 21 or 23. You can make face the problem. Okay, so this solution I will try to discuss in the next class. So in the meantime, you also try to make the LST map using Landsat 8 imagery for year of 2022 or 23. Okay, then we can easily get the face the problem. Okay, you did not get the proper result, and why you did face the problem, then I describe the next class about that. Okay, so it's a assignment for you. You also try to make the LST map using Landsat 8 for year of 2022 using the same algorithm try to use, but you face a problem. But this problem solution I also do for the next class about that. Okay, and this is the process we already discussed about the removing the cloud and cloud shadow from here, and then calculate about that minimum, maximum, or average. So now I talk about the next topic. This topic is that DEM data. Okay, so basically in Google Earth Engine platform, we are also get the different types of DEM data or star we can easily get from here. So in this time, I talk about the NASA SRTM DEM data. Okay, which is the 30-meter resolution for NASA SRTM dataset. Okay, for using the DEM data, there are a lot of analysis for the hydrological analysis we can do in Google Earth Engine platform. Lot of hydrological analysis, catchment area or drainage basin. So there are a lot of things we can easily do using the DEM data. But in this time, I show you that how we can easily create the hillshade map, salt map, aspect map using the DEM data, and also download the DEM data and also make the hillshade map for any specific region. Okay, so let's go. So just simply search here NASA SRTM.